sources of error. Sources of error in regulators. So, even though I will be talking in perspective with the linear regulator, but all these sources of error are applicable for switching regulator as well. So, the first one, can anybody tell what could be the sources of error? Okay, so loop gain, offset, that is one source, one of the sources of error, but I will put that at the end. Before that, I want to just cover the simple sources. So, we know Vref. So, if you have any error in the reference, that will directly get reflected at the output. Then mismatch in feedback resistor, correct, that will be error in your beta. Offset. Okay, so now for this particular we are not looking for any stability or AC analysis. So, I will just draw a very simple regulator. R1, R2, so this is your V out. So, if I call it A01 and the gain of this is A02. So, what is A0? A1 into A2, correct. So, equivalently you can draw this plus minus Vref okay, same thing. So, I have taken the output stage inside and it will look like a single amplifier. So, what is your V out in terms of Vref? Vref over beta, but it is really not beta actually. Yeah. When you say beta, you consider A naught equal to infinity. So, in reality your gain is so closed loop gain equal to okay. So, if you and this is if beta A naught is much larger than 1, and that is why we make it independent of open loop gain, correct, or A naught, but this is not true in reality. Your A naught is infinite. Okay. Okay. So, if example, if let us say beta equal to half, okay, your Vref equal to let us say 0.6 volt. So, V out we know we are expecting 1.2 volt, okay. But if we go from that equation, V out equal to A naught over 1 plus beta A naught Vref, and assume A naught equal to 100. Now, your V out will become 100 over 1 plus, how much is that? 50. How much is this? 100 into 0.6. Multiplied by 1. So 1 point, yeah, so 1.76 roughly, that is 1.176, huh? Minus, so error is how much? Minus 0.023 volt, which is close to 2%, correct. So, we have introduced 1%. So, if you look at the gain A naught 100, okay. So, if beta is 1, 100 will gain of 100 will correspond to almost 1% error, but since beta is amplifying your output, so 1% becomes your 2%. So, if your beta is let us say even smaller, then your error will be larger in that case, because your loop gain will, product of beta into A naught will further reduce, okay. So, which means in order to reduce error, we should have large beta A naught, okay, or for smaller beta A naught must be increased, okay, usually more than 60 dB also. So, if you have a 60, your A naught is 60 dB, which is your 1000. So, 0.1% error in feedback voltage, which means 0.2% error in the output voltage. So, 0.2% is not that large, as usually if you are let us say less than 1%, then it is acceptable, but you have to make sure your overall error means including your line regulation, your load regulation and error in the Vref, everything remains within your specification, okay. Whatever error is basically specified for that particular voltage, if it remains within that, then it will be acceptable, okay. And that is why we try to improve on each and every thing, so that you minimize the error, so that you can get more room for other errors or for your transient response, because we know it is going to undershoot or overshoot during transient. So, if you remain very close to your steady state voltage, desired steady state voltage, then you get more room for your line and load transient, okay. So, we cannot afford, so if your regulation limit is plus minus 5%, that does not mean that you can afford to have a 5% error, because your line transient and load transient will make it to go beyond 5% and it will go out of regulation. Okay. Second is your VREF. So we know V out is VREF over beta so any error in VREF will directly affect your V out. Okay. So if your beta is smaller, then again a smaller error in VREF will get amplified. So error is more for smaller beta. Correct. Again the same thing which we looked at the loop gain. So if you have a 1% error in the VREF, that means you have a 1% error in your feedback voltage, and now when you are looking at the output, that is amplified by your 1 over beta factor. So if it is a 2, then it will become 2% error in the output. So that is why having a smaller VREF is not very good in terms of error. So let us say you want 1.2 volt output. So one way, like you have a VREF 1.2 volt and have a beta 1. Another way is have a VREF 0.6 volt and have a beta 2. So having a beta 1 may have a lesser error compared to having beta 2, or VREF 1.2 volt will give you lesser error compared to 0.6 volt. Okay. Then third is your mismatch. So your beta is R2 over R1 plus R2. And we know V out is VREF over beta. So assume R2 and R1 have plus minus delta R error. I am assuming same error, it may be different also, but just for simplicity. So what will be the worst case? Both will have plus delta, or one will have plus delta and other will have minus delta? Different, because if both have a same, then they you cancel out, so there will be no error as such. If both are moving in the same direction, so that ratio will not change as such. Okay. So R2 becomes R2 plus delta R, and R1 becomes R1 minus delta R. So now your beta will become R2 plus delta R, and plus minus delta will cancel out. So this will remain R1 plus R2, and I can say that. So your beta, I will say beta dash. Okay. One plus okay, which I can say this is your beta 1 plus, I can call it delta beta. So your beta is increased by a factor of delta beta or delta R by R2. So if this has again R2 has, let's say, 1% error and R1 has a minus 1%, then your beta will be increased by 1%. Okay, and we know that V out is, so now V out will become V ref over beta dash, and that will have same amount of error. Okay, and where does it come from, that mismatch? So this is your feedback resistor. So this is your V out, R1, R2. So what happens when you lay out them in the chip? Okay, so if this is your R1, this is your R2. So what happens, this when you place the basically conditions at that particular location may be different than the what is seen by the other resistor. Okay, one thing might be like your due to the process you have some mismatch, and that may come due to the error in the basically non-ideal effects in your process. So one may have a slightly smaller width or length compared to the other, that will come from process itself. That's the one thing. Other thing is your temperature gradient. So this might see a different temperature compared to the other, even though it may be a very small, but you have to consider that depending upon how much it is affecting. Even if it's a 0.1%, it will have some effect in your output. Okay, so 0.1% error it's being introduced in your output. So we try to match them, and we apply some layout techniques to make sure they are matched, and just like common sense. So what we do, we split them in pieces. Instead of having a single R1, single R2, we split them in pieces and distribute equally, so that on an average the total resistance is seeing the same effect, and they will cancel out. So error is averaged out and becomes close to 0. Okay, so we'll talk about the layout techniques for matching, and this is applied in not only resistors, but in your amplifier you need to match the input pairs, diff pair, because the G1 if GMs are different, then it will again introduce error or offset in the output. Okay, or you will have an input deferred offset, which will get translated into error in the output. So those offsets and everything is reduced. So first thing, we precautionary, we try to reduce the error as much as possible by design and by layout. Okay, so when I say design, basically by properly choosing the transistor sizes and how you split them. Instead of using a two single big transistor, we split them in multiple transistor and distribute them in the layout, so that error is averaged out. And same thing we apply with the capacitor and resistor, the same concept. So common centroid is the one technique. Then interdigitized means you interleave the, so let's say I break them in 4 pieces, R1 and R2. So put one piece of R1, then adjacent to that R2, R1, R2, R1, R2, just like you interleave them. So the error will be averaged out in that case. So we try to place them as close as possible. That's the one thing, so that if you put one guy here, other is like 100 micron away, then they will the difference will be much large in all the conditions, whatever is seen by each resistor. So we'll talk about those layout techniques later, but that's a one way. And then after that, if you are still not meeting your accuracy requirement, then we use some techniques in the design itself, like offset cancellation, to reduce that or completely cancel the offset, bring it to almost 0 actually. Okay, so it all depends on what kind of accuracy you are looking for. Especially for these regulators and all those, you may not require offset cancellation quite often if you have taken care in the design and layout. But think about ADCs, like 10-bit, 12-bit ADCs, they require accuracy of like hundreds of microvolt or so. So there you cannot afford to have any offset. So there you have to cancel offset. There is no other way, because achieving those kind of accuracy with layout, it's not possible. Just by layout you cannot cancel everything.